All right. Good afternoon to everyone. So I found that a lot of misconception or miscommunication rooted from you didn't like listen closely to what I say, or you didn't read closely what I wrote. Okay. So please pay attention to what I say and what I wrote. Okay. So most importantly, you need to listen to what I say. Okay. Uh so a what do I mean? So if you can't understand me, right, straight away, stop me. Okay. So please listen to everything what I say. Okay. If you are not clear about the instruction, please ask. All right. Okay. So don't think that you can work out yourself. You can't. Okay. Because some of the lecture content, right, I can determine myself. Okay. If I choose to spend more times on this topic, then this topic will be tested in future. Okay. So although we are following a textbook, but I can modify myself. Okay. So really, you need to pay attention to what I say. Okay. If I say something wrong, you just feel free to point out, and then we will fix it together. Okay. Not a big deal. All right. Um, regarding the project, right? Jingbo advised me to have the cover page, assignment report. Okay, your assignment and also the turn it in report. Okay. So later I will send out the cover page. Okay. So first you submit your assignment to the turn it in. Okay, and then get out the report. And then you compile a cover page, your assignment, and a report, and then I'll open out a Moodle link and then you submit there. Is it fine? Okay. So turn it in, you just get a report out and then compile together. Is it clear? I will write out the announcement again later after I post it up with the cover page. Is it clear? Clear? Okay. 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 I'll write it out as well. In Word inside our group. Okay. It seems that we spend quite a lot of time in partial derivatives. Okay. Hopefully we will finish up by today. So I still want to deal with this open, close, bounded concept now. Okay. So if you have any problem, you should point out immediately. So I will reintroduce them again. Okay. 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 So why we deal with this closed and bounded uh, idea? Okay. Primarily, we have this Clairaut's theorem. How to spell Clairaut? How to spell Clairaut again? Is this the right spelling? Can someone help check? Can someone help check whether this is correct or not? The name. Clariut. Sorry. Clairaut. Okay, thank you. Okay, so first of all, the open set come out in this theorem here. If this is continuous on open set, then sy equal to fyx. And second one is the S-string value theorem. Okay, what does extreme theorem say? If f is continuous on a closed and bounded set V, then f obtain both an absolute maximum point value and an absolute minimum value. Okay. All right. So I also got feedback from you guys that there's not enough examples, right? Okay. So what's the example for extreme value theorem? Okay. What's the example for extreme value theorem? In where's Qi Feng there? Qi Feng? Yan Jing? Thought they are here just now. Buy one, free one. Huh? Buy one, free one? Lost two or? Lost two eh? I don't sell them, but okay, it's okay. Okay, so uh this theorem doesn't make sense to you. Okay, so let's see how this extreme value theorem makes sense, right? Okay, so you should think of this extreme value theorem from one-dimensional case. Okay, from one-dimensional case, what do we have? Okay, so you will think that it's weird why when I talk about two-dimensional, you want me to think about one-dimensional. So this is really generalization from function of one variable. Okay, that's why I keep linking back to calculus 1. Okay, what does calculus 1 do? Okay, let's say you have a continuous function. Okay, right? So if you cut it at a closed interval. Okay, you consider a closed interval AB. Okay, you look at here. Can you find the maximum, absolute maximum point or not? Can you manage to find the maximum, absolute maximum point within this A and B? So this curvy line is our function. Can you find within A and B the maximum point of this function? Can you find it? You can, right? Okay. So what's the other possible way? The maximum can occur at the boundary. Okay, makes sense? So last time we say what? You need to check stationary point. You need to check boundary point. Okay. And also you need to check the place where differentiable doesn't occur. Okay, where it is not differentiable. Okay. So how to extend this theorem to two-dimensional? You just imagine the domain become two-dimensional. Okay. In fact, you can do n-dimensional. Okay. So you just replace the domain here into two-dimensional. Okay. Right. Can you imagine? So let's do generalization. So let's do generalization to this x, y, and z. Okay. Similarly, you also have function above. You either got a line, or you got a surface. Okay. And then you find the maximum point again. Okay. Again, so what's the close set here? Okay. So you also need to pick some region in this case. So since your domain already become two-dimensional, right? Okay. So in general, you also can find a closed region. Okay, a closed region. A closed region. It's a bit ugly. Maybe closed region here. Okay. And then you look at everything at the top. And then within this box, you find which one is the maximum point of this function. Does it make sense? Make sense or not? Make sense or not? Okay, in one-dimensional case, you have this one line here. Okay, then you check above this line, above the domain, which one is the maximum value? Okay, and in two-dimensional case, you look at a closed region, and then you check what is the maximum value of your f. Make sense? Yeah. Okay. So now we want to like define what this word really means. Okay. What this word really means. What is open set? Okay. Open set. And then what is closed and bounded set? Okay. Hopefully I can done within this hour. So to know about open set, right? You need to know about open this first. Okay. So first of all, what are the setting we have now? What are the setting? What are the setting here? The setting here. So what are the setting here? Where does this open set lies? Where does this closed and bounded set lies? Huh? Where's the domain of this function? Huh? I give you choice, R or R2. R or R2? Okay, so let's think about it. So for first one, right? Does it make sense in R or not? Do you have XY variable in R? No, right? Doesn't make sense. How? So in the function of one variable, you only have derivative with respect to one direction. But now you have two direction. Okay. So for the first theorem to make sense, you have to stare at least two dimensional. I think what I said is quite makes sense, but seems like you guys confused. I'm not sure why. Any question or not? For question? Did I say something doesn't make sense? So in clearer theorems, okay, you have partial derivative with respect to x and y, right? So you have two direction. So for two direction to work, your domain have to be at least two dimensional, right? Okay. So first, this open set here have to work. So the setting here is actually just tell you the answer. This setting here is in R2. Okay. So we talk about open set in R2. Okay. Okay. How about extreme value theorem? Okay. So this setting here can be in R or R2. Okay, like what I say, you have a R version from calculus 1. Okay, now we want to study the R2 version of it. Okay, so in our notes, right, we also care about closed and bounded set in R or R2. Huh? R or R2. Brian, R or R2? Huh? R2, huh? Okay, R2. Okay, so we need to ask ourselves what are the open set and closed and bounded set in R2. Okay, so to know about open set, right, you need to know about open disk first. Okay, what's an open disk? Did we define this before? Okay, so to define a disk, right, like defining a circle, I need to tell you the center and the radius. Okay, so I need to tell you the radius, I need to tell you the center. Okay, so an open disk are all the point, okay, in R2 such that they are delta different from my center. Okay, you should think about circle. Should think about circle, but I fill in all the thing inside. I fill in the circle. Okay, I fill in the circle. So how you should think about it is you have a circle of radius delta, and then you fill in the circle. Properties of radius delta center at AB. Okay, so far so good. So far so good. Okay, so when this is equal, right? When this is equal, you get a circle. But I fill it in. All the points that are less than delta are also 1. Make sense, huh? Okay. Okay. So good. So how about next one? Open set. Okay, open set in R2. Okay, let's call it X. Okay, so what's the open set means? What does open set means? So what's open set means? Okay, so I should write like this. The set S is open. Okay, so open is an adjective. So what kind of sex? What kind of set? Sorry, what kind of set? What kind of set? Sorry, what kind of set? What kind of set is open in R2? And so it's an adjective. What kind of set is open in R2? So, how you describe a set? What's the thing inside the set? Set contain what? Element. Good. So you need to describe what kind of element is in there. Okay. So the set is open in R2 if for every element in X. So why I can put my X as element in X as XY? Why can I do that? My set is a subset of R2. Okay. So subset of R2 if so discrete math, right? If it is subset of R2, every element in X is also an element in R2. So how you express element in R2? Sum XY. Make sense? Okay. So if for every XY in X, there exists, okay, there exists a disk with radius delta centered around XY is also such that this is contained inside X. Okay, so how you picture this? Okay, you don't understand this, it's okay, but you need to read this sentence and then I will explain why. So let's say this is open. Okay, this set is open in X in R2 is open. Okay, meaning what? Meaning for every point I take, right? Okay, I can find a ball that's completely contained in my set. Okay, so if I take this point here, can I say that I take this ball? This ball is already outside my X. So it is not open, can or not? Why? Uh, why? I find for this point, right? This point is inside my S, oh, correct? It's inside my X. But I found this that is not contained in my original X. Does it contradict or does this violate the open condition or not? Because open condition say I can find a this which is completely lie inside my X. Right? Okay, but this one doesn't completely lie inside the X, right? So how? Does this violate discrete math? Huh? Does this violate or not? What do you mean by not a subset? What is not a subset of one? Who is not a subset of one? The this, the green this. The green this is not a subset. So does this violate the open condition or not? Ah, yeah. Does this violate the open condition? Open condition says what? You need to take every point from the X. Okay. Every point from the X. You need to find a this that is completely lie inside your S. Okay. So now I take a point from my X. I found a this that's not completely lie inside my X. Does this violate open condition? Why? Say again. Is what? Is all. Okay. No, not quite. Not quite. Not quite. Mm-hmm. All the point lies inside the X. Sure, I already take a point lie inside the X. And then now I find a this. Right. I need to so to show the set is open, what you need to do? You take a point inside your X, you find a this which is completely lie inside the X and contain XY. Right? Correct or not? Correct? Okay, but now I take a point in X and then I found a this which is not completely lie inside my X. So my question is, does this violate the open condition? Not quite. Not quite. There's something to do with the quantifier. The key part here is the quantifier. Yeah, there is a this. I just show you that I cannot find it. Doesn't mean that there is you you can't find it forever. Okay. So can you find a this around this plane such that it is completely lying inside or not? Can you do it in this diagram here? You just pick smaller radius. Okay. Okay. So, but now you need to check for all x, then this is your work. So you need to check for all x, everything. And you need to show for every x and y, you can do this. Okay. Okay. So why this uh idea pops up? Okay. So this is also a generalization from R. Okay. Or the open interval in R. This is a generalization of open interval in R. Okay. So if you take an open interval 0 to 1, right? Okay. If you pick any point between inside this interval, you can create a sub-interval which is of length non-zero. You believe me or not? Let's pick any number from this. Pick any number from this interval. Pick one. Mei, pick one. Pick one number from this 0 to 1 interval. Huh? Half. Half. Okay. Sure. Let's take half. So can I create a sub-interval that contains half, which is non-zero size? Okay. Who is behind 定语啊？可以啊。 huh? Okay. Yeah, so you noted, right? So how? 0 from where? From 0.7? 0.7 should be here, right? And then from where to where? From 0 point, I mean, or from 0. Oh, okay, from 0 to 0.7. Yeah, good. Okay. Although this is a big interval, but it's fine. Okay. So you can see we can find another open interval inside our 0, 1 interval that contains 0.5. Okay. So the interesting part is, how about you pick something really close to 0 or 1? Okay. Let's say I pick something from 0.0002. Okay. Can you still find the interval? Can you still find an open interval that contains this number here? Okay. So maybe I can find, for example, 0.00000. So no, maybe 15 is enough, and then 0.00025. Okay. So we are trying to capture these properties inside my open set. Is it okay? Okay. So this is a generalization of this open interval into open set. Okay. Okay. And then next, we already define what is open. We define what is open this open set. Okay. The next thing we can define last time, if you still remember, is a set is closed. Okay. What does a set is closed mean? Similarly, closed in R2. Okay. The set is closed in R2 if the set C is equals to R2 take up X for some open set S. Okay. So you might think that this one is like how to say, it's like very set theoretic. Okay. Just set theoretic. Just you take the whole space and then take out some open set. Okay. So in the textbook, right? So equivalently, I'm going to introduce some new notion. So please bear with me. If C contains all its boundary point. Okay, so I haven't defined what is boundary point here means. So I will say here a boundary point of C is an element in C such that for every this around, let's call this boundary point a name. What name? Let's pick what name to pick? If we use, maybe let's call it AB. Okay, a boundary point of C is an element. Is an element AB. Okay, let's call it AB. Such that for every this at B, okay, for every this at B, the this contain points in C and points not in C. Okay. So you should think of why these two are equivalent. Okay, why is this equivalent? Okay. In the textbook, they give this definition here. So in my lecture, I give this definition here. Okay, but these two are equivalent. So why are they equivalent? Why are they equivalent? So I define close in R2, right? Okay. So this is also a generalization from one-dimensional. So what are the closed set in one-dimensional? Closed interval in R. Okay. Let me show you example in R, right? Okay. So closed interval in R. Let's pick 0, 1 again. Okay. 0, 1 live in where? Live in the whole real line. Okay. Let's draw it out. This is our real line. And then here is our 0 and 1. And then so on. Okay, so on. And then so on. So where is the boundary point of 0, 1? The interval 0, 1. 0 and 1. Okay, why? Why do you claim that 0 and 1 is the boundary point of the interval, closed interval 0? What range? Say again, rephrase again. What do you want to say? Uh-huh. Okay, so wait, what's that? Okay, so I asked him, so what is the boundary point? He said the boundary point are 0 and 1. So when you explain why it is true, you should explain from the definition. So the definition says a boundary point of C is an element AB in C such that for every disk around AB, okay, that this will contains point in C and points not in C. So how you translate this into real dimensional? Okay, so how you translate this to real dimensional? A boundary point of 0, 1, interval 0, 1 is an element in the interval. Okay, he already picked the element 0 and 1, right? 0 and 1 is in my interval, such that for every disk, so this in two-dimensional is a disk, in one-dimensional is a interval, not range. Okay, so you need to start learning this word. Okay, so this is another interval. Okay, open interval. Okay, open, right? Just now we define open this. So open interval. This open interval, no matter how you pick, because for every, right? For every open interval you pick, this open interval must contain point inside the closed interval 0 and 1, and also contain point outside the interval 0 and 1. Okay. So is this true for these 2 points here, 0 and 1? Is this true or not? Does everyone get? Still don't get? Get or not? Don't get? uh, who? What name? Who is the name behind? Shunling. Beside 袁家 beside 袁家，玉晶哈，玉晶是玉晶啊，就是玉晶。Okay，玉晶。So where you confused? Too many words cannot follow. Too many words. Okay. Slowly. So I will explain again by drawing it. So now I need to explain. Okay, for every open set I take, right? Open interval I take around 0. Okay. Does this open interval must contain point outside my set C and also contain point inside the set C? Let me maybe drop this also. Then make this boundary point to other color. Okay. So since Siyu say that 0 is a boundary point of our set C, is it true that I pick any open interval, that open interval must contain point outside C and inside C? Can follow? Can follow now? Okay. Is it true? Can you pick a disk that entirely lie outside C or inside C or not? Cannot, right? Okay. If you do that, then you exclude the boundary point. Okay. So around this boundary point, so my open interval, my disk have to use the point as a center. Okay. So you can see that away from this center, I go inside C. Away from this center, I go outside C. Okay. So this is a boundary point. This is boundary, right? You have to cross the boundary to go into another country. Once you cross the boundary, it's already in Singapore. You cross the boundary, you're already in Malaysia. Right or not? Cannot say that I cross the boundary, I still in Malaysia. Impossible, right? Then that's not the boundary definition. Right? Okay. 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 Yeah. So this is the example in real. So we want to extend this idea to different space. Okay. Now next space we do is R2. Okay. Is it okay? So maybe you should ask me, right? You should ask me how this first part here get demonstrated. So you say that 0 to 1 is closed. Okay? 0 to 1 is closed because it contains all the boundary points. Okay? Similarly, you can show that 1 is a boundary point. So there are only 2 of them. So let me write down boundary point of C are 0 and 1. Okay, and it contains in the closed interval. So how you write it? So how you write 0, 1 as a set of R take out some open set. So what open set you need to take out? Here. So you have a whole real line. Okay. You need to take out something to get this closed interval. What's the interval you need to take away? So you take away. Okay, so let me move things. So you take away negative infinity to 0. That's all. Union 1 to infinity. Okay. So you can show that these two are actually open. Okay, these two sets are open. Open of union set. Union of open set is still open. Yeah. Question. Yeah.
Right close set. 1 to infinity left close set. This is then close set from the first definition.
Okay, say again. Say again.
From first definition,
yeah.
The set is closed.
The complement and the open set is closed. Okay, yeah, sure. Yeah. Open set 0 and 1.
It's complete.
Okay. You mean this, is it? Okay, good. Very good. Very good. Very good. Okay. So why is this closed? You ask, right? Okay, so question. Why is this closed? So why is this closed? Okay. So if you are not happy with this first definition, right? First definition already tell you close, right? You're not happy. We got equivalent definition, so we should check the other equivalent definition. So does it contain all the boundary points? Does this set, okay, this union here contains all the boundary points? What are the boundary points? Okay, so let's draw this picture out, right? Okay, because these things are very close to topology already. So you should draw the diagram out. Okay, so like this, okay? Instead of considering closed interval between 0 and 1, so we consider this kind of interval, right? What are the boundary point for this new set here? What are the boundary point? What is the boundary point when you step across, you reach another place? When you step the other way, you still lie in the original set. What is that point? What's that point? So your set is S. Sorry, the green part, right? The green part. So where are the boundary point? Is 2 a boundary point or not? No, right? You step in here, also S. Step in here, also still. So which one is the boundary point? Just 1. So at 1, if you pick any this around it, right? You contain point. It is in the set and outside the set. Okay, that's all. Also 0, 0 and 1. Okay. And you can prove that these are the only boundary point, and it contains all the boundary point. Okay, make sense? Okay, but why we introduce this? Because we want to capture this closed interval property. Okay, is it clear? Yeah. Okay, at least clear at the R example. So you need to think about the R2 example. Okay. Yeah. Okay. So next, let's keep finishing first. I think we will spend whole lecture doing this. Okay, let's finish the bounded. Just finish this bounded and then we'll. So what's the bounded set in R2? How to define a bounded set in R2? Do you know how to define a bounded set in R? I think we encountered this before. So how to bound a set in R? Everything in the set is bounded above and bounded below by some number. But in 2-dimensional, how many things you need to control? Of course, many, but because it's okay. For example, 1-dimensional, you also have many things to control, right? But you can use a variable to capture all of them, right? So in 2-dimensional, how many variables you need? 2. Okay, 2. So you need to control the 2 variable. Okay. So a set in so let's for what name to pick. So a set P in R is bounded if for every element in P, okay, that exists, let's pick 4 number to bound it, right? Upper bound, lower bound, okay, for both. So let's pick what? M, M, N, M, N, okay, in R, such that S is bounded above and below by capital M and small m, and Y is bounded by capital small n and B. Does that make sense? Make sense or not? Okay. So you got 2 coordinate, right? So these 2 coordinate you only can pick from this range. Okay, so this is bounded set. Okay. Okay. Agree or not? Or lost already? Hey, Ryan. And any can follow? Can. Okay. Okay. This is bounded. Okay. So But equivalently, right, in your textbook, okay, a set P in R2 is bounded if for every xy P, there exists a this, okay, there exists a this such that xy is in the this. Okay. So the claim is these two are equivalent. These two are equivalent. Okay. If you can bound two variables, right? Okay. It's equivalent that you bound all the point within a this. Can picture or not? Can you picture? Can. 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 How about let's do some drawing? Okay, kindergarten drawing. Can or not? Okay. So from the first example, right? Okay, first example, we have a bounded set. Okay, bounded set. So we have a little m. So our x is bound by little m and big M, somewhere like this. Okay, so you only can pick x from this range. Make sense? Still make sense or not? Okay. How about y? Y bounded by small n and big N. So small n maybe pick somewhere here, and then big N pick somewhere here. Okay. So what are the possible points inside your set? Huh? Something within the rectangle here. Make sense or not? Make sense, right? If you pick this boundary point here, what is this? This is m and n. Okay, but still less than m on x, less than n on less than or equal to n on y. Make sense? So we have these. These are the possible points in our set, and then we say that this is a bounded. Is this bounded or not? Bounded within a region. Make sense? Okay. Can follow up. But second definition say we also can bound this set by this. How can you find the this? Can you find a this that bound this set or not? What? Cylinder? Cylinder. No, I need this only. Yeah, I just need this. Can this rectangle here bound by this? Cannot. How? So we just find a large enough these to cover it. Makes sense? But this is still finite, right? Finite, right? Finite radius. Okay. So we can find a this to cover it. Okay, with a finite radius. Okay. So why these two definition is equivalent? Let's say my set is contained in a this. Can you find a rectangle that bounds this or not? How? So you pick a rectangle that is larger than the circle. This. Okay. And then you keep doing this, doing this. This is topology. Okay. Yeah. Okay. Okay. So these two definitions are equivalent. Yeah. So when you read my lecture notes, when you read textbook, so don't confuse. They're actually the same. Yeah. clearer now? Chiffon. Oh, following. Can you bound? So I ask you a question. Can you bound a smaller disc with a rectangle or not? Ah, can. Okay. Yeah. So we can take a larger. So it's like what? In 3D, in 3D, right? Okay. You can take a ball and then find a box to cover the ball. Okay. And then have a box. You can find a large sphere to cover that box. Okay, and so on. Okay, so they are equivalent. Okay. Right. Make sense? 曾勇 ha. Hey, what's your name? 永之 ha. Okay. Make sense? Okay. And for yeah. Okay. So I spent so much times here, right? You will expect some question inside assignment about this thing. Okay. Yeah. Okay. So yeah, I mean you are not alone. Okay, you all still can ask me, right? Or you can ask the others. What? Why laugh? Why laugh? Why laugh? What difficulty? No, I mean, you pair, right? Okay, you need to learn something. Okay, you need to learn something. Otherwise, it's wasting money. Okay, I don't like to waste money. Okay, yeah. Okay, so you pair, you come here to learn. Okay, if you learn nothing, then wasting money. If you don't want the money, just banking to me. Yeah, don't give to this school. Give to me. Okay. Yeah. Buy better iPad. Okay. Uh, okay, let's take a break and then we come back and then we should finish partial derivative and then we'll start with multiple integral today. Okay, let's come back at 205. 205. Sorry. 305. 305. 或者因为会差时间吧。那个时间那个数据。他就是把历史文字后来你要换去你要在的地方，发现可以打开哦。好，或者是或者用在下面一个假设，第四个可能，然后我这边第二批，你要知道它是。 một cái OK， 你看它是好的一哦，你不要跟我讲，你是不好的，不是好的。是吗？是真的不要OK， 你可以说we follow the convention of this book。哎啊，眼睛。好了。
对，等一下那些我的 equation 写那些像我的班 L，像我的班个 F bro 什么减 L 对 L 这样东西啊，还那个啊，这个不用紧的了。就是假如像我讲，我 define 一个 function，我们减 L 一个 priority function，我们减 L 对 L 这个机制啊，还那个啊，不用紧啊。
哦，不用紧啊，不用紧。
只是那些 introduction 可能那些句子。
Hey, okay. One thing I also want you to learn, learn to prioritize your work. Okay. Don't procrastinate. Prioritize your work. Which one need to do first? Which one need to do first? Okay. Please prioritize your work. Otherwise, everything gets stacked up. Okay, prioritize your work. Okay. So last time we stopped at string value theorem. Okay. So how to find string value theorem? First, you need to find the. Let's bring out the example. So how to use string value theorem? First, you need to start with a closed and bounded set. Okay. Right, just now we just recall it. Okay. First, you start with a closed and bounded set, and then how to find string value theorem? String values. Okay. So those string value points are the points that are stationary. Okay. So what are the stationary points? Or the critical points? Okay, actually they are the critical points. What are the critical points? First of all, are the stationary points. Okay. So remember how you do calculus 1, how to find maximum minimum point. Okay. Stationary point, first of all. What is stationary point? The gradient is 0. Good. Okay. But now in our case here, our gradient is a vector, right? But vector also give you a point in R2, which is what you want. Okay, a point in R2. So stationary points, gradient length equal to 0, find the point. And then singular point, where the point is not differentiable, where the function is not differentiable. And also you need to check the boundary point. Okay, check the boundary points. Okay, so you need to compare all the values of this point. Okay, all the values of this point, and then decide which one is bigger or smaller. Okay, decide the absolute one, the most, the maximum, the most, the greatest, and the smallest. Okay, so far okay, quite straightforward. The next one is how to decide local maximum and local minimum. Okay, so in calculus 1, you also check using second derivative test. Okay, so in R2 case, we also have second derivative test. Okay, So what's the theorem? So the theorem says that if f has a local maximum or minimum at a point, and the first order partial derivative of f exists there, okay, so meaning it is differentiable, then the gradient of x naught y naught is 0. So if f has a local maximum or minimum, it is also a stationary point. Okay, this match up with calculus 1. Okay. Okay. So once you have this so you see this theorem, right? The condition is if you already know the local maximum or minimum, then you compute the gradient there, it is 0. Okay. It doesn't tell you how to find it. Okay. But it just says that if you have it, when you test the gradient there, it must be 0. Right. So can you devise a way from here? Can you go backward or not? Can you go backward? Right. Because our purpose is to find local maximum and local minimum. Okay. But this direction is if you already have a local maximum and minimum, then you know that the gradient at that point is 0. So can you devise a way to find local maximum and minimum? Ideas? Any ideas? Any ideas? Oh, is my question clear or not? Super worried you don't get what I asked. Huh? Okay. And then can you decide whether it's local maximum or minimum or not from this theorem? No. Okay. But at least you know that it is either local maximum or minimum. Or not. Okay. There are two choices, whether yes or no. Okay. So that's why we have this second derivative test here. Okay. So if you check that that's a stationary point, okay, and your f has continuous second partial derivative, then you find this d. Okay. This d here is a bit complicated. Okay. It's the second derivative of f multiplied by the second derivative of y minus the square of the mixed partial derivative. Okay. So it is a bit complicated, but if you look close enough, right? Okay, what is this? You multiply two product of two numbers, and then there's a sign in between, sign change. It is close to determinant. In fact, we can write it as determinant. Okay, so what is the determinant we can write here? So we can write f x x here, f y y on the diagonal, and then f x y f x y. Okay, so you can see that actually this determinant here doesn't seem symmetric. Yes or no? Usually we have fxy and fyx. Okay. In fact, we can replace by fyx on one of them. Which one? Usually the first one is row or first one is row. Okay, like this. Actually, we also can write like this. Why? When is fyx equal to fxy? Continuous when the second derivative is continuous. Okay, but you have continuous second partial derivative now. Okay, yeah. So that's why we, instead of computing fxy, fyx both time, actually we just compute once, they are the same. So yeah, so you need to combine all these second derivative together to compute the d. Okay, so this d here, okay, so this d here is a number or a vector after evaluate at s naught. Why not? Vector or number? Eating. You have something to say? So what's this? is a number. Okay, we evaluate the function at a point already, and then we just take the multiplication and then take the subtraction. So you get a number. So how to decide local minimum and local maximum? So you need to make sure that d is greater than 0 and the second derivative with respect to x is also greater than 0 at that point, then it is a local minimum. Okay. So does this match up with the second derivative test in calculus 1? So when the second derivative is greater than 0, it is a local minimum. Okay. But now you have two conditions to check. One is d, the other one is second partial derivative of x f with respect to x. So local maximum here a bit weird. So is it weird? Yeah. So when d is greater than 0, you need to make sure that the fxs is less than 0. Okay. Then it is the local maximum. If d is less than 0, then we cannot decide anything. Okay, it's a saddle point. It is not at any extreme value. Okay. So these are the local maximum, local minimum, local maximum, and then saddle point. Okay, saddle point. You know why this is called a saddle? You know what a saddle is? It's the seating you put on the horse. Right? Yeah. So you can sit here. So there's a horse here. It's okay. It's a topologically equivalent. Okay. Yeah. Okay. So yeah, you sit on the top and then there's a horse. Okay. So why we call this a local minimum, local maximum? Any idea? Why are they called local maximum or local minimum? Why are they locally? Why are they local? Why are they local? Can I call it the extreme maximum or extreme minimum? Why not?
Yes, within a neighborhood.
Uh,
Yes, within a neighborhood. That's not point.
okay, it is within a neighborhood of S not one. So you don't know about larger domain. What happened to other places? Okay. Within this neighborhood, you know that this is a. But let's say if you extend again, you have lower point, right? Okay. Make sense? Okay. Yeah. So the only thing you can say is either local maximum or lower minimum. Local minimum. Okay, let's do some example. Do some example here. So let's find the local extrema and saddle point of the function. Okay. So, what's the first thing you do? You start with finding the what point? Qifeng, how you start to find a local extrema point? Differentiate, and then what's the point? Differentiate 2 times. Okay. You haven't get the point yet. Why you differentiate 2 times? What's the point you need to get first? Stare. What point? Okay, so how you remember this? When you add the local maxima and local minima, right? Okay, why are they called stationary point? Anyone think of it? Why is it called stationary point? Stationary is what? Stop. Okay, why stop? Why stop? So if you put a ball here, right? You can imagine that this ball will slide down, right? If you have a plastic bag and then you take the corner up, right? Your ball will slide down. Okay. How about this local maxima? It's also the same. Go to the top, it will stay here. You can imagine the trajectory of any balls, okay? If you play any balls, like basketball, football, or I play badminton, okay? So when the ball go to the highest point, highest point in the trajectory, the point will stop for a while and then come down, okay? So you can see that this local minima and local maxima, right? We prefer local minima, okay? Because at local maxima, although it will stay, but I push a bit, it already dropped down. If you perturb a bit, the ball drop down. But if you are at the local minima, it is stationary. If you perturb a bit, it still come back. Perturb a bit, still come back. Okay. Yeah. So these are called stationary points. Okay. So you are also stable at this point, but if I perturb a bit, it's easily for you to just hold. Okay. So don't stand on high place. Okay. 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 Yeah. Be careful. Yeah. Okay. So to find local extrema, you need to find the stationary point where the gradient is 0. You don't move anymore. Okay. So what's the gradient? I think we all forgot how to find gradient already. Stress stuff. Okay. How to find gradient? First, you need to find del f over del x and del f over del y. Okay. So how to do this differentiation? What is del f over del x? Del f over del x. You keep y constant, differentiate with respect to x. So what do you get? X cubed minus 4y. And then del f over del y. Yeah, don't be shy. Don't be shy. What is del f over del y? I cube over x. So now you want to find stationary point, set gradient equal to 0. Okay, so what are the points you will get here? You will get 4x cubed minus 4y equals to 0. 4y cubed minus 4x equals 0. Okay, in the end, what do you get? You will get y equals to s cubed. Okay. And then what can you do? Let's call this name. So from 1, we can get 3. Okay. Let's call this 3. Then next, start 3 into 1. Sorry, 2. Okay, sub 3 into 2. What do we get? We get 3 to the power 9 minus x equals to 0, which is just x times x to the power 8 minus 1 is 0, which implies that how many roots do we have? We have x equals 0 and x equals to plus minus 1. Actually, there are 9 roots here because this is 9 order, but all the other roots are not in real. Okay, because by fundamental theorem of algebra, you have the degree, the number of root equal to the degree of your polynomial. But we are in the real now, so we only have 3 roots, 3 real roots. Okay, 3 real roots. Okay, what else we need to compute? So we know that these are stationary points. So we need to check the discriminant, the D. Nice. So we need to check the D. So what's the definition of D again? D is fxx at the point x0, y0 times fyy at the point x0, y0 minus fxy at the point x0, y0 square. Okay. All right. So have we really got the stationary point yet? So we only know that we have x equals to 0, x equals to 1, x equals to -1. So what are these y? Okay. So if you put back to your equation here and find your y should be just y equals 0, y equals to 1, y equals to -1. Okay, so these are the stationary points. Okay, maybe this is not appropriate yet. So let's write down the point. So 1 is 0, 1. Yeah, sorry, 0, 0, and then 1, 1, and -1, -1. Okay, -1, -1 are the stationary points. Okay. So how to compute fxx and fxy? We just continue differentiating. How about we compute differently? Fxx, xx is what? So fxx is just 12x squared. Okay, right. And then fyy is also just 12y squared. Okay, and then fxy is what? Ying, what is fxy? -4. -4. Okay, good. -4. Good. Very good. So you can see that if you do fyx, right, you also get -4. Okay, so they're equal. Okay. All right. So so what is fxx? So we need to compute this point here. So let's tabulate them. So we have how many points here? So we got 0, 0, 0, 0. Okay. We got 0, 0. We got a 1, 1, 1, 1, -1, -1. Okay. So critical point live in R3 or R2? Critical point is a point in R2. Okay, the domain. Okay, we care about domain. So what is D in this case here? So D in this case here, what have we computed? What's the formula for D? D is 12x squared times 12y squared plus 4. All right? Fair enough. Fxx times fyy minus fxy. Okay? Is it question? Oh, square. Good. Very good. Square. Square. So we squared it. So we got 16. Good. Okay, we have square. Minus. Oh yeah, minus. Correct. So okay, let's just write it down so we know what we are doing. So minus 4 squared. So it becomes 16. Okay, good. Okay, very good. So what is FSS? So it's equals to 12x squared. Okay, and then conclusion. Okay, so what is the D for 0, 0? What's the D for 0, 0 in this case here? Minus 16. Good. So what's the D for 1, 1? 12 square and then minus 16. 12 square minus 16. 1 to 8. Okay. Minus 1 also get the same answer. Okay. So we have first one less than 0, both greater than 0. Okay. So when D is less than 0, right? Just now we said that that point is a saddle point. It's a saddle point. How about 1, 1? What's the f(x)(x) at that point? So when D equal to greater than 0, we still need to differentiate whether f(x)(x) is greater or less than 0. Okay. If it is greater than 0, you get local minimum. If it is less than 0, you get local maximum. So in this case here, we get 12 for 1, 1. And we also get 12 for -1, -1. So both of them are greater than 0. So both of them are local maximum or minimum? Minimum. Okay, minimum. Okay. Yeah. So the shape is something like this. Okay. So you have 0, 0 here. Okay, it's a saddle point. So saddle is like this. And then 1, 1 at here, and then -1, -1. Local minimum. Okay. Yeah. And then if you cut out the level curve, you will get something on the right. Okay. You can see that this height here is increasing from this dot here, increasing, and then all the way up. So you can see that this is the dot, and then you have this circle, 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 and then kind of mix here, and then go up again. Okay. Yeah. So this is really a generalization of one-dimensional calculus. Okay. Generalization of one-dimensional calculus. You just need to check more things now. You need to check D first before you check f(x)(x). Okay. Okay. The next part here is called the Lagrange multipliers. Okay. For this part, you don't need to know why is true, but you need to know how to use it. Okay. Maybe later you will see. In future you will see why this is true. Okay. So suppose we want to find extreme value of a curve. Okay. But now there's one condition coming in called gxy equal to k. Okay. There's another curve coming in. So subject to this constraint here. Okay. So once you have these, right, you want to find extreme value. Okay. But subject to another condition. Okay. This is equivalent of saying that their gradient is scalar multiple of each other. Okay. About why it is true, maybe it's not so important yet. So you just remember that once you have you have a problem of finding extreme values, okay, for two variable function subject to some condition gxy equals to k, then they have to satisfy some scalar multiple equation. Okay. Okay. So let's see how we use this. Okay, how we do this. So how we do this? So let's try this. Okay. So the question here says that I have a rectangular box without a lid. Is to be made from 12 meters square of cardboard. Find the maximum volume. Okay. So if we put XYZ as a length times width times height, okay. So what's the volume of the box? Let's call it B. So what's the volume of the box? What's the volume of the box? XYZ. Okay. So you want to find the maximum value of this function here. Okay. But this maximum value here, what's the maximum volume? You can go forever, right? Don't you? Right. I put as long as possible my length. Okay. But you are not allowed to do that because this box here is controlled by the material you use. Okay. This area you use. Okay. So what's the surface area here? What's the surface area you have? What's the surface area you have? What's the surface area you have? Hmm? So you have two sides with ZY, okay? Two sides with ZX, one side with XY, because there's no lid. So altogether you have 2 times YZ plus XY plus 2XZ, okay? And then this has a fix, okay? What's the fix of our surface area? What's the question asking? What's the bound of our surface area here? What's the total surface area of our cardboard? Huh? 12. Okay. Yeah, it's okay. It's just, yeah, 12. Okay. So, uh, so we are finding an extreme value for a function of 2 variable. Okay, now it's 3 variable. Okay. So it also work for 3 variables. And then subject to a constraint. Okay. So we need to set del f x, y, z equals to lambda of del g of x, y, z. Okay. So it must satisfy this condition by the Lagrange multiplier. Okay. You need to satisfy this. Okay. So you need to solve a bunch of system of linear equation. Okay. So maybe you can check my answer. I just write it out. You can use your inspection to see whether I get the right equation or not. So you need to compare del f del x with del g del x, del f del y with del g del y, and del z del f del z with del g del z. Okay, so we will get this equation here. Okay, so how many variable you have? 1, 2, 3, 4. 1, 2, 3, 4. X, Y, Z, lambda. Okay, so we should get at least 4 equations so that it is not underdetermined. We have another condition here is the condition from the surface area. Okay, you can see that these system of linear equation kind of not linear, right? Because you got y times z, right? Not linear. Okay, so what to do? And what you can do is you can play around with this. So one way to play around with this is let's show you this trick here. Maybe you can have other method to solve, but you can somehow see the symmetry with this equation, right? Okay. So let's say if you multiply 1 with x, and then multiply 2 with y, and then multiply 3 with z, okay? What you will get is xyz equals to lambda xy plus 2xz, and then so on. Maybe this method sound a bit ad hoc, right? Okay, but you really can see that if I fill in this part here with right variable, then I can equate everything on the right hand side. Make sense? So if I multiply x to the first one, I get x, y, z. If I multiply y to the second equation, I get x, y, z as well. Okay. And then I multiply z to the third one, I also get x, y, z. So I can get another set of equation. Okay. And so why is this set of equation useful? You need to do another inspection again. So you can see that actually x equals to y equals to 2z will work. Then would solve this equation here. Yeah. So what do I mean? What do I need to say here is actually when I present this kind of thing to my other class, right, you will ask, will exam come out with this question or not? So sometimes I don't know how to answer them because sometimes question can get tricky, but really depend on what the lecturer want to test you, right? So I want to test you whether you know the concept or not, or you know how to calculate or not. It's a different thing. Okay. So what you can do is try learn as much as possible. Yeah. Try learn. What I mean is try learn why I present this method. Okay. Why this work? Okay. Try and see why this work. Okay. Instead of saying that I want to get marks, I need to learn this or that. Okay. Try see why this work. Okay. And that way you can learn more stuff. Yeah. Okay. Okay. So up to this stage, what can we do? We still haven't solved XYZ yet. Okay. Can we do small simplification or not? Okay. What else we can do? Okay. So you can see that we reduce x to y and then y to 2z. Okay. So everything we can express in 2z now. Okay. So which one is better to do? So we can sub 5 into the surface area constraint. Okay. Such that we get that 2 times 2z times z plus 2z times 2z plus 2 times 2z times z equals to 12. Okay. Why? Because x is 2z, y is 2z, x is 2z, and then so on. Okay. So altogether, what do we have? So we have here 12z squared equals to 12, implies that z squared equals to 1. And then z can be 1 or minus 1. Can z be minus 1 or not? Why? Huh? The length, okay, you cannot have negative box, right? Okay, so z equals to 1. Okay, so when z equals to 1, so everything will be clear. So since x is equal to 2z, we have x equals to 2, y equals to 2, and then z equals to 1. So their unit is m because we start with 12m squared just now. Okay, so what does this say? This says that if you pick your length, okay, if you have a 12-meter square cardboard, okay, the maximum volume you can get is by making your length into 2 meter, your width into 2 meter, and your height into 1 meter. Okay. If you do other method, you will get less height, less volume. Okay. Okay. Let's try one more question because this one is kind of new stuff for me also. So find the extreme values of this function on the restriction of this circle here. Okay. All right. So what do we have? We have this function fxy equals to x squared plus 2y squared. And then f of, let's call it g of xy equals to x squared plus y squared minus 1 equals 0. Okay. But what's the form of our gxy? The form of gxy we need to get is what? So let me recall it. Just now we say that gxy equals to k. Okay. For some k. So what can you do? You can take this, or you also can take gxy to be x squared plus y squared. Okay, it doesn't really matter. You believe me or not? Doesn't really matter. Okay, because after you differentiate, the constant term will disappear. Okay. Okay. So next. So we need to start with this Lagrange multiplier again. Start with Lagrange multiplier. So what are the del f del x you have? Del f del x is what? Hello, hello, hello. Too slow, too slow, a bit slow. You guys a bit slow. Del f del x is what? 2x. Okay. Del f del y or y. Okay. How about del g del x? Huh? 2x. Del g del y? Huh? 2y. Okay. Do you guys know how I get this equation or not? We are comparing the two vector here. Okay, we are comparing the two vector here. So let's write it out. Del f, del x, del y, del f, del y, and del g del x over del x del y. Okay, so you have three variable here. Do you have another equation or not? Where? Where? Still slow, a bit slow. Huh? Not possible. Not possible. What did he say? Not possible. Did you say not possible? Okay, not possible from this gradient, this vector equation, but there's one extra condition from the question regarding this x and y. There's one extra condition from this question here. So it's the condition from the G. Okay, the condition from the G also control the x and y. Okay, good. Okay, how to fix this? How to fix this? So from one, I think from one, this one is easier, not as hard as last time. So from one, what can you do? You can factorize 2x. Okay, 2x times 1 minus lambda equal to 0. Okay, implies x equals to 0 and lambda equals to 1. Okay. So what are these points here? So you need to check these points. So when x equals 0, what do you get? X squared plus y squared equals to 1, right? So y squared equals to 1, which means y equals to plus minus 1. Okay. So when lambda equals to 1, what do you get? You have 4y equals to lambda 2y, right? From here, you will get 2y equals to 0. So y equals to 0. Okay. So when y equals to 0, what are your points? So this implies that x squared plus 0 is 1, which means x is equal to plus minus 1. Okay. So how many points you have now? So you have 0, 1, and 0, minus 1. And here you have 1, 0, and minus 1, 0. Correct? Correct? Correct. Yep, question. Why? Why this part here? Okay, so this is from 2. So I should say this one is from 2. From 2 here. Because when you sub lambda equals to 1 here, you get 4y equals to 2y. You subtract 2y from both sides. Yeah, good. Yeah. Which one? Oh, this one, yeah, correct. This is del G over del I. Good. Yeah. Del G. Yeah. Anything else? So far, okay. Okay. So we found this for do we call this stationary point here? Yeah. So we solve this stationary point. Okay, critical point. Sorry, critical point. Okay. So we need to determine whether these are the upstream value or not. Okay. So we need to determine whether these are the upstream values or not. Okay. So we still need to compute the height. Okay, the value of this number. These are just points in the domain. Okay, you need to compute the value of f at that point. Make sense? Okay, these are just critical points. Now you want to decide whether they are extreme values or not. So, what is f of 0, 1 and f of minus 1? What is f? X squared plus 2y squared. Okay, so what do you get for 0, 1? A bit slow, eh? AIT can count faster. Oh. Huh? 2? Okay. F01 is 2. F0 minus 1 is 2. Okay. And then how about F10? 1. F minus 10 is 1. Okay. So what do we have here? So we have that these 2 points are maximum. And these 2 points are minimum. Okay. Yeah. Okay. Yeah. Okay. So how does this demonstrate inside our diagram here? So x squared plus 2y squared, right? It sketch out a surface. Okay. And then you have a restriction of this circle. So what does this mean here? Okay, what does this mean? So this means that if you look at the circle here, okay, and then you look at how this circle get mapped into this function here, okay, do you know how to do this? So you take all the points lie on the circle, okay, apply f to those points, okay, then you will trace out another circle inside your surface. Can everyone see this? So you take a point here. This point is described by sy, right? Okay, you fit it into your function f, and then you check the value of that point. Okay, check the value. Check this value here. Okay, okay. So it traces out another circle around this surface here. Okay, but this circle here is no longer the fixed circle. It's go up and down. Okay, go up and down. And then we found that at 0, 1, 0, 1, 0, 1, where's 0, 1? So 0, 1, where's 0, 1? 0, 1, 0, 1. So 0, 1 is here. Okay. And then 0 minus 1 is here. Okay. And then here is 1, 0. And then the other side is minus 1, 0. Okay. So we see that at 0, 0, 1, it is 2. Okay. 0, 1, it is 2. Okay. This is the highest point. 0 minus 1, it is also 2. Okay. On the other side, you cannot see quite clear. And at 1, 0 is 1. Okay. 1 is here. And then on the other side, you also get 1. Okay. So for the both 0, 1 and 0 minus 1 are the maximum of this curve. And then when you go to 1, 0 and minus 1, 0, it is the minimum. Okay. So this diagram, how you see this, you can try and smash this diagram down. You smash it down. Okay. So you smash it down. So after you smash it down, right? These two circles here, the first circle here, The first circle here represent the level set of this function at this point here. Okay, at the point k equals to 1. Okay, and then the other pink circle here is the level set where the function equals to 2. Okay, and then you can see that this graph here runs in between these two circles. Okay, try to imagine. Okay, how to see it is you smash this surface flat from the top. Okay, use a brick. Yeah, you can use a brick and then smash it flat down. You know, you guys recycle the item, right? Because the thing is too long, right? You need to smash it, right? Yeah, that's how you smash it. Yeah, smash it flat. Okay, smash it flat, and then you will get something like this. Yeah, question. You can try. I can help you translate. I don't understand. Sorry, I don't understand. Say again. Yeah. Which one? This one? This one. First. S square plus 2. What? Oh, here. Okay, this circle, yeah. We map it up. Yeah. Hmm. You can, but okay. So she's asking. Okay, let me repeat. See correct. So you're asking, can we map all the point on this surface down to R2? Okay, this is not calculus question anymore. This is other question. Okay, so can we map it? Sorry. Can we map everything on the surface down or not? Okay. Okay, so of course you can, right? You just map it to 0. But I think the question is, can we map 1 to 1? Yeah, meaning every point go to different point. Okay. So if you can do that, what do you get? This is a bijection. Okay, bijection between two surface. Okay. So what is the two surface? Bottom is R2. Okay. At the top is also R2. Right, remember? Okay. So I think in this case here, what's this shape? Anyone know this name? I forgot what's the name. Okay. Let's just ignore this and then we imagine that this shape here will go forever large. Okay. Then you can. Okay. You need to figure out what's the inverse trend. Okay. Yeah, you can. Yeah, you can. Yeah. So you need to figure out the inverse map. Okay, I'm speaking of this surface only. I'm speaking of this surface. Let's say this surface can go forever long, infinitely extending. Okay. So what you are thinking is like you have a cloth like this. It's like you go to bed, right? So you take a blanket and then you cover everything. It's like that. Yeah, so how you cover your blanket, if you flip here, flip there, then you change the sign. Yeah, very good. Yeah, so this is Lagrange multiplier method. Okay, so you want to find an extreme value of a function subject to some condition gx1. Okay, then these are all similar question already. We will post it later. Okay, so far any question before we end this partial stuff? We should go a little bit faster in the integral part. Just now I met your probability lecturer. He also mentioned to me, but I just I got one student do that question. 实验博, right? Yeah, he do a more generous version. He integrate. What do you integrate again? Is it e to the minus x over a? Huh? ax squared. Okay, so he do a more general version. Okay, so what you get is you have square root pi over n over square root n. Okay, over square root. Yeah. Yeah. So he do a more general version. Yeah, we will see it in his project. Okay. Yeah. 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 Okay. So let's take a break and then we'll come back for multiple integral until 4:10.
那时候呢 project 怎么改？
你 project 应
嗯，
该没有了，应该
没有了。
好了。
所以是对着黑然后就这样子。
等一下，我要你们compile那个 cover page，我会发一个拿出来，但是你们一定要是交到 Turnitin 把那个 project 那个 report 弄出来，他会直接发给你们不？那个什么东西？
是按进去 download 可能。
要自己 download。
对。然后那个配音我不知道你的 setting 是怎样，因为我们 foundation 就要给到很多次啊，前3次是等大概2-3分钟就拿到，可是过了3次过呢，每次要等12个小时、24小时、36小时。
那是 Turnitin 自己的 setting 是吗？
我也
好像不能调哎。如果那个金宝有跟我讲过这种事，
对，
可是好像我没有好调哎。
对，调不了，对，
但是还不行，
所以就不能一
下子
调，对。
OK，其他人知道吗？
我不知道，不过 foundation 应该都懂。
OK，叫我跟他们讲。真用 here 真用。嘉瑜，sorry，wrong name please。要问什么？
如果是我的 project 里面证的那个结论，老师你不清楚的话，你怎么判断我正不正对呢？
我只要看你的真的步骤对还是错就行了。干嘛？什么问题？
我中间那步化简，那步化简，我不太懂得我怎么画的。
OK，你不太懂你怎么画，但你是不是
中间那个过程，
那
个因为就是推导到那个公式，其实到那一个式子那里已经是够的了，因为我求的是那个用球形就是那个坐标去，然后我已经把那个式子列出来了。
OK，
然后但是我看到它有另外一种表达形式
OK，
就是然后我就直接跳过去化简了。
然后
但是中间那个化简过程我没写。
中间那个化简过程你没写？
对。
OK，
最主要的是我也不知道，
你不知道怎么写。你如果有时间就搞清楚它，没有时间也没办法了。
因为这个我发现，网上就是找这些论文那些也找不到，就是感觉没有人。
它是很复杂的东西吗？
也不是很复杂，我感觉不是。
你写得出吗？
它那个公式的那个原理我大概是明白了，我是明白的，但是
它如果复杂的话，你私下把它写下来吗？
行。就是它那个公式怎么？
如果时间不够也算了吧。
最主要的是那个准确性，就是
准确性怎么会准确性？
因为
他们不是已经证过了？
因为我就是找不到前人证过的东西。
这个不是应该要有人算过的？
没有，我现在一直找不到。我只能找到相近的。
在算什么？现在？
用球形公式，用球形坐标以球形坐标系来把 x、y、z 带成一个单数方程，然后来求它的 arc length，求它的弧长。
OK，
OK，
所
然后
以你说那个图场算出来，不知道是对还是错的答案。
是的，我用了就是其他几个理论，就是类比它以及我查阅到的资料得出来的那个公式，我觉得它是对的，但我没办法保证，因为前面也没我没查到有相关的资料，有哪位专家证过
啊，
就很怪。
这样子能够看你中间有没有输出。
因为相当于是一个类比法。
或者你能不能够算一个我们已知的东西，然后来比较？
已知的，
已知，
我就是通过就是二维的那个，
能不能算一个已知的，然后我们来比较？
我算了一个，就是在举例那里举一个比较好理解的例子，是吗？
对，就是你可以用另外一个方法算到好了，这样你就可以
就是让那两个相等，它就是对的。
当然相等不代表你的中间过程是对的，但至少
它相对正确一些。
就是至少我们能够有东西比较，只能这么说的。只能这么说。
谢谢老师。
好，规则 ，OK， 规则 here。成银期，成银期。亡灵经 ，I think 亡灵经 disappear for a long time already。亡灵经，who is 亡灵经 friends？ Who know 亡灵经 ？Don't know。Okay. I think last time he also not here, right? Last Friday. Ling Jing. Is Ling Jing here now? Don't know. Yi Zhou, Xie Yi Zhou. Okay. Yang Liu Qing. Okay. 真诚。翁庸志。Okay. I almost know all of you already. So good.
比例等等。
哦，你看这个怎么找哈？只能够 test 吧哦。
这个只能 test 吧，
因为它不理你了。
你要看到这个东西，那你最好就是丢给电脑做。
不理你哦，你讲丢给电脑做，什么电脑可以 solve 这个不理你了？
可能你丢给你去做你们的话，应该做得出来。
你们个 method 不是 solve 那种一点多这样的东西，
很难看的。
怎样能够算到这个整数？可以算得出来，还是它只是 approach 这个整数？
对 approach，每个出来就 approach。
没有啦，这题有点其实只是 show 给你看啊，
我就大
题怎么做？
差点跳的。
所以这题怎么办呢？这题吼呀，你看你把这个等于嘛，对不对？这样你 lambda 可以切掉，切掉过后这两边怎么等于呢？你就 test 一 test，只能够 test 吧 ？I mean，我觉得正常的题目是这种啊，但是这种就有点 tricky 啦，我就说，
像上面有一个正方形啊，啊，对，
对吧？
就是
不是
不过他没给我图形，这样我是不是就找不到？
你要自己把它画出来哦，你自己 determine 它的 size。
可是我要懂这个长怎样是？
这个啊，你懂这个长怎么样？这个长怎样？第二我刚才画的那个东西啊，它 x 是从0到3嘛，对不对？然后0到2嘛，然后它整个 range 的
就在它的帮，
不是它的帮。你看是不是讲 f 的东西，真的东西一定也要投对吧？
没有 post 到，我没有被提到。
什么？哦，这个 blackboard 的我有 post 不是？
没有啊。
有啊 ，blackboard 的有，我只是还没有整理。因为我这边还没有整理，因为我还没有把这些东西写好。我今天讲的比较好，然后把整个东西写好来，然后就整个播出去。
可以。
OK。什么？
我不懂，我还要不要再讲？
你要写什么？写啊。
是要写专业语这样。
比较好啊。
可是已经超过了。
没事啊，没事没事没事没事啊。
没事吗？
但是你不要废话太多
我
哦。
没有很多，我觉得我
你算法很多
我那个废话多。
不会啊，我如果有废话，我早就跟你请了前期。
多超过，因为我那个有快退了，
可以啦，就那样就好了，
因为我之前
就那样就好，那样就好，不
然后
要再讲
我就改成OK。
就好，那样就好。加你先呗，感觉你一直听不懂我在讲什么哦，就是你不懂我的要求，
懂了，
你懂没？
讲呢我就讲，就是要破一个题。
但是怎么没有做出来？
那个爬虫的话是直接把那篇放上去，要加那个 cover page。
要，我等一下会再
那个 page 要附上，
我会发一个 announcement，然后发给你们那个 cover page。
这只要一起交。要 combine 吗？
对，红炮起来下。
可是我有个问题，可以告诉我们，因为我点开之后发现我进不了你给的那个。
我再发一次，有的再发一次邮件。
那你不是讲来不及改？
对啊，我就跟你讲了。但是我说你以后啊，以后，对，因为我看到你的考卷也有这样子的类似问题，你感觉我不知道，你可能我感觉你不知道题目在问什么，所以这个是你要克服的一个东西，你明白吗？你要克服这个东西，我不知道你怎么克服，但是
我有
你要
去读，我就是
有去读
你的意思是，
啊。
你要我去找有兴趣的，可是在班上没有 proof 过的。
还有东西你好像读漏了，就是我比较 rigorous gap，就是比较就是数学方面的，你明白吗？不是只有你兴趣的，你明白吗？对吗？合理吗？
那你又发了一遍。
对，我再发一遍。
但他的公式算是可以 proof 的一个东西。就那个 x 平方的 a 平方。
但是你要想啊，这个东西和我们学的东西有什么关系啊？是不是你自己想一下，对吗？对吗？对吗？是不是合理？但是我是说，现在已经没有时间了，也不用紧啊，你能够做什么你就做什么，可以吗？可以啊。
然后我看到你有讲，就是我不是有写一到5面内，你把后面那3个弄在一起。
啊，对，和结合一下，不要分这样多。我是不是把什么结合啊？我是把身体结合嘛，对不对？我没有我把什么东西结合？你看一下我把什么东西结合？那2个应该都是在讲 theory 的东西，对不对？你看一下呀，你看一下我把什么东西结合在一起呀？袁家有收到吗？袁家，哎，你是谁？啊，原来你是聊聆听。可以，对，你在，我刚才看到你。对，对，
时速的那个非常
什么是什么？
发了什么？
哎，不然等一下我先开始先，没发到哈。
明白也是。
啊？OK，
直接有 P 和那个 ID 吗？
看一下啊，我也不知道去哪里找，我没有用过。等一下再回来看，我要开课啊。你的话就你有问题啊？
我不知道是不是只有我。
是咯，如果我 email 给全部人不是更好？但是我是说，我研究一下，
好的，
我研究一下，我不是很熟。OK。Okay, let's keep go on. Keep going with this multiple integral. Okay, so let's review this definite integral. Okay, so definite integral. Why is it definite? Because we are integrate over a definite interval. Okay, interval. So we look at an interval from A to B, and then we try to compute what is the area under the graph. Okay, what's the area under the graph? Okay. So, how do you start computing this area of graph? Anyone know or not? What's the first principle? Huh? Huh? Say again. Huh? Riemann sum. What is Riemann sum? Okay. So my question is, what is Riemann sum? What is Riemann sum? What's the idea of Riemann sum? What's the idea of Riemann sum? How this idea started? Or why you do that? Why you want to do that? I know. So yeah, sure. It is to calculate the area under the curve, but why it works? Okay, I don't want to ask why it works. So what's the origin? Let's say I give you a straight line. You know how to compute the area of this under this. So why do you know it? Why do you know? Why do you know? Do you need Riemann sum here or no? Why no need? Why can you directly calculate? Yes, this is a square. Okay, simple object we know how to calculate. So this definition starts from the area of square or area of a rectangle. But you can ask why this is the area of rectangle. I don't know. Okay, so we just need to pick a place to start. Okay, we start with an area of rectangle. Okay, we start with an area of a rectangle. Okay, so we only know how to compute the area of the rectangle. But this, for arbitrary function, right? This is a curve. So where to find rectangle? Okay, how we find this rectangle out of this curve, this area? How to find? How to find? Okay, so the idea is like what Ying say. Okay, Ying say. So if you have this, okay, let me not distracted by these shapes. So let's get this done. So let's describe the idea. So let's have some graph, something like this. So we want to find a rectangle. Okay. So maybe I'm a bit stupid. I pick this rectangle here. Okay. I pick this rectangle here. Okay. I know how to find this rectangle, right? So I just take the height and the length. I get the rectangle. Does this represent the area under the graph or not? No, right? Okay. Obviously, we have something extra here. Okay. Okay. But we can replace it by some other rectangle. Maybe replaced by this one, and maybe replaced by this one. Yeah. Okay. Maybe I use another color. So I replace with these two triangle here. These two triangle here. Does this two triangle represent the area on the graph or not? No, but it approximately better than just now, right? Because you have less extra stuff. Okay? And then you can keep dividing until what? Until you get the thin strip. Okay, so let me draw something. So you can divide this further, maybe like this. Okay, and then you divide further, something like this. Okay, so you can imagine that when I reduce this rectangle, right? Okay, so let me. Wait for me. So if I reduce this rectangle further and further, okay, I can kind of approximate my area better. Okay, and then I take limit of this. I'm adding more rectangle and more rectangle. Okay, adding more rectangle, approximate better. Okay, until all the rectangle become a strip and fill up all the space under the area. Can you imagine the process or not? Imagine the process. Okay, so that's why we take the limit of the number of rectangles go to infinity. Okay. Yeah. Okay. Okay. So yeah, I didn't mention about upper sum, lower sum, those things, because those are just specific construction. So I just tell you the general construction. Okay, so in this case here, so we recall that the definite integral by definition is the product of the value of f at some point star. Okay, what is this star here? What does this star here mean? This star here means this is some point within the interval. Okay, so for example, we have, so let me spell this out. So we already learned infinite series, right? So let's spell this out. What are these terms? So these terms are, can someone tell me what is the first term? Slow, too slow. What's the first term? Fx. Not yet. Fx or what? What's the point x? X. Where's the running index? Where's the running index? 1, right? Okay. 1 star. Okay. Delta x plus f of x2 star times delta x, and then so on. Okay. Yeah. So where does this x1 star lies? This x1 star lies inside this interval here. Okay. So the interval of the first interval is x1. So the first interval is x2 star to x1 star. Okay. So let me write here. So wait. So this is a x1 minus a. So x1 star lies in between a and x1. Okay. And then so on. Okay. You can pick any value here. Okay. In between the interval. Okay. Any value. Do you believe I can pick any value and then when I hit limit, this thing will work? Yes. Why? Why you so confident? How you got project? Okay. Yeah. So his project work on this Fourier series. So Fourier series, when you define the integral, you need this definite integral, and then when you take limit, you need to deal with this rectangle. Okay. Yeah. So this doesn't matter you approach from top or bottom. Doesn't matter you approach from upper or lower. Okay. You will always converge to the same thing. Okay. Because for upper one, you need to pick the largest f. For the lower sum, you need to pick the lowest x inside your interval. But in this case, we don't really care. Okay. They should converge as well. Okay. Okay. So now again, this is one variable, right? So we need to extend to 2 variable. Okay. So can you imagine what happened when we extend to 2 variable? The domain here become 2-dimensional. Okay. So instead of integrating this rectangle, what are you integrating? You are integrating a rectangular boxes. Okay. So you are integrating over rectangular boxes. Okay. Okay. So let's see. So this is what we call the volume or the double integrals. Okay, volume, right? You fill in the part under the surface, so you got the volume. So let R be a rectangle with side parallel to the coordinate axis. Okay, so you see this notation come out again. Okay, did we met this notation before just now? A bounded set. A bounded set. Did we? Hey, hello. Did we make this notation just now when we discussed about bounded set? Yes or no? Yes, right. There's this A, B, C, D such that the element is bounded above or below by this number. Okay. Okay. So similarly, what we do to the one variable case, we subdividing the subdividing the interval. Now we also dividing our rectangle. Okay, but how you subdivide? You also subdivide the length and width. Okay, you just so just now we subdivide an interval. Okay, so we subdivide an interval, right? But what we do now is we subdivide a rectangle. Okay, how do you subdivide a rectangle? So you just cut on the x-axis, cut on the y-axis, and then cut on the x-axis, cut on the y-axis, where you make more rectangle. Okay. And then you can consider all these sub-rectangles. Okay. So what's the example here? So let's look at some examples here. Okay, so our Riemann sum here, right? We have two variable now. Okay, we have two sum now. Okay, just now we only sum over one variable. Now we sum over two variable. You can cut it on the y direction. You also can cut it in the x direction. So x direction should be like this, y direction like this. Okay. So this is the domain picture. This is in the domain. Okay. So when you go to the graph, okay, which is domain plus codomain, okay, then you will have this 3D shape coming up. So let's say this part is your f, okay, your fxy. Okay. So how you compute the area under the graph? You need to consider all the rectangle, okay, all the rectangle, and then you try to take limit of increasing the rectangle, increase until you get single strip below this area, and then you add all of them up. Okay, okay, make sense? Okay, so this is the idea. So if you just look at the rectangle, it will be something like this. So you can see that, what can you see? What can you see here? You can see that this is like discrete. Is this discrete or not? It's like staircase, right? Discrete. But the staircase for disability is this one, slanted. Okay, it's like continuous. Okay, so if it is discrete, right, it's hard for the wheelchair to go up. Okay, but if you add more staircase, like more stairs, okay, you add more stairs, infinitely more stairs, then it becomes something smooth. You see it? So you see, so here is like something discrete, like a Lego, right? So if you make this rectangle smaller and smaller, and we really can't see the difference anymore. That's why it becomes some differentiable or smooth surfacing. Okay. Yeah. Okay. So we are using discrete stuff to compute something that is continuous. Make sense or not? Yeah. Okay. So when you take limit to infinity, this discrete object becomes something continuous. This is our approach to study continuous object. Okay. Okay. So what's the double integral? Okay. So let's start with a function of two variables. Okay. That defined on a closed rectangle R. Okay. So meaning our domain is a rectangle R. If the following limit exists, okay, so can you see that this is really similar to the Riemann sum? Okay, instead of one variable function, we have two variables, and then instead of difference of partition, now we have difference of area, right? Because we have two-dimensional, we have rectangle, so the area multiplied together. The length multiplied together, you get area. Okay, area multiplied with the height, you get volume. Okay, make sense or not? Make sense? Okay, let's repeat again. So in this part here, right? Why we say it is an area? Because this is a change of a length and then multiplied by the height. So you have length times height. So you get area. Okay. But now in the double integral here, delta A is the area of your rectangle domain. Okay, and then you plus your height, multiply your height, so you get a volume. Make sense? So that's why we call double integral a volume integral. Okay, then there are two things here. Two limit you need to take. You need to subdivide everything on x, subdivide everything on y. Okay, so you make the rectangle really small, really small. So you should ask a question: does this limit order matters or not? Right? Does it matter? Okay. Why we always ask this? Because not everything in this world is commutative. You cannot always commute. It's not like number 2 times 3 equals to 3 times 2. This is not always true one. Okay. In fact, generally it is not true. Okay. So most of the time we are working with commutative stuff, but most things are not commutative. Okay. But in this case here, in fact, if you take any order of limit that should converge to one thing if it exists, you can show it. Okay. So if it exists, then we will say that f is integrable. Okay, integrable. It is integrable. And in that case, we will write double integral of f dA, okay, over the closed rectangle. So this is just a notation. This is just a notation. This is just a notation. The actual meaning is this one. Okay. So when you do this notation here, this is what it means. Okay, you take the limit of the rectangle, subdividing the rectangle to really small. How you subdividing the rectangle? You increase the number of your rectangle. Okay, then this is called the double integral of f over r. And then this following is the definition. Yeah. So if fxy is always greater or equal to 0 on this domain, the double integral represents the volume of the solid under the surface and above the rectangle R. So is this clear? Is this clear? So let's say, what do we have? Let's say we have this hemisphere. Okay, hemisphere. You know, okay. So you know about sphere, right? Okay, what's the formula for sphere? S squared plus y squared plus z squared equals to 1. Okay. So if we want to restrict to everything greater or equal to 0, we can just cut the bottom part. Okay. We're left with the upper hemisphere. Okay. So if we compute the double integral inside this hemisphere here, what you really get is the volume of the solid hemisphere. Okay. This is what it's trying to say. Okay. So you fill up the surface, the area under the surface, the volume under the surface. Okay. And above the rectangle. Or in this case, we are not rectangle, we use a circle. Okay, so let's take an example here. Okay, let's take an example. So try and evaluate the following function, square root 1 minus x squared dA over a rectangle by interpreting the double integral as a volume. Okay, so first you need to understand what is the function square root 1 minus x squared. What's this function here? Yeah, what's this function here? Square root 1 minus x squared, right? Should sound a bit familiar. Okay, if I play around with this equation, right, what do you get? You get f squared equals to 1 minus x squared. Okay, actually these points are the points that are satisfied by the unit circle. Okay, these points are the points satisfied by unit circle. But what's the matter of this square root thing? Okay, what's the matter of this square root? So this square root here only pick out the point that are on the positive. Okay, so you have a circle. Okay. You have a circle. Y equals y squared plus x squared equals to 1. Okay. So what's with y equals to square root 1 minus x squared here. It picks up the positive y part. Okay, it picks up the positive y part. Does it make sense? Make sense? Right. Because after square root, right, you should come out a positive number if you take square root of a positive number. Okay. Okay. So what you get is the top part here. So let me draw it. So this is the y equals to square root 1 minus x squared. Okay. 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 So this function here, right, doesn't depend on, oh, sorry, the function on the right doesn't depend on y. So on each y, you have this hemisphere. Imagine or not? Hemicircle, not hemisphere. Hemicircle. Okay. So let us draw it up. So let's draw it up. So what is this trying to do? Let's try. Okay. Where does this hemicircle have to face? How to form this hemicircle? How to form this hemicircle? So you should think about this axis here, right? Okay. So when S increase here, so you produce a value in a Z direction. Right? So do you agree that we have a hemicircle here? We put this in. So here is -1, here is 1. Semicircle. Can you imagine or not? Can you imagine or not? Imagine or not? So let's try number, right? Try the number. So when x equals to 1, okay, fxy is equals to 0. Okay, it's here. Okay. And then when x equals to -1, fxy also equals to 0. Okay. How about when x equals to 0? fxy equals to, hey, slow, too slow. 1. Okay, so here. Okay, so you can go between these. Okay, so this not, I mean, y doesn't affect the value of z or value of the function. Okay, so you have these hemicircle keep going infinitely forever. Okay, so in this case here, you will form these what do you call this? Half of the cylinder. Half of the cylinder. Okay. Can understand this shape or not? This shape now. Okay, better. Okay. So once you get this shape here, this question asks about this particular domain here. -1, 1, 2, -2, 2. Okay. So where does this covering? So you cover from -1 to 1. Okay, how about use this one? -1 to 1. Okay. Okay, -1 to 1. Okay. And then -2 to 2 on the y direction. Okay. Yeah. Going sleep already. Fall asleep. Okay, so that's fine. So yeah. So what to do? How to compute this? Okay. I didn't tell you how to compute double integral unless you try and go to do the rectangle thing and then do the limit. Okay. But what we can do here is you use this line here. Okay. This line here. We don't know why it is true, but it is given that it is true. So we can use it. Okay. So the double integral works if my fxy is greater or equal to 0 all the time. This is what we have. this fxy here is always greater or equal to 0. Okay. And then this double integral will represent the volume of the solid under this surface and above the rectangle. So do you know how to compute the volume of a half cylinder or not? What's the volume of a cylinder? Volume of a cylinder is what? Pi r square h, the volume of cylinder. Okay, pi r square h. Okay, so half of it is half time pi r square h. So what's the radius and height for this case? So by statement above. While I'm writing, right, please tell me what's the height and radius in our case. Radius is 1, height is 4. Good. Okay, so it's equal to half time pi times 1 squared times 4, which is equal to 2 pi. Okay, so we bypass the limit in this case here. Okay, we don't want to do limit, right? Kind of hard. Okay, how about this? So given this function here, piecewise function. Okay, this is a piecewise function. Okay, it is 1 when x is in between 0 and 3, and y in between 0 and 1, and 2 when x is in between 0 and 3, and y is in between 1 to 2, and 3 when x is in between 0 and 3, and y is in between 2 and 3. Okay, so what's this shape here? Okay, so you can observe that the x is always in between 0 and 3. Okay, so we fix our x in between 0 and 3 here. So how about we start with redraw this diagram. Let's see we get the same shape or not. So x, y, and z. Okay, so we fix our domain from 0 to 3. Okay, but when y is from 0 to 1, our f is just 1. So we have a height 1 here. So what do we have? So let's draw it like this. So about, okay, let's draw it like this. Like this, like this, like this. Okay, throw this away. Okay, so let's keep this dashed line to indicate the height. Okay, from 0 to 1 here we have this plane. Okay, you know why we have plane? Because the fxy equals to 1 doesn't depend on xy, right? So no matter what point you take inside here, you always get height 1. So you get a plane. Is it clear? Is it clear? Okay, no matter what xy you stay inside this domain here, you always get 1. Right? Okay. Similarly, if you go from y equals to 1 to 2, okay, the height increase, you go to 2. Okay. Similarly, you got another plane at the top here, for example. Okay. Okay. But not that this y doesn't include 1. Okay. So this side here is actually dash. Okay. So is it okay if I put y equals to 1 here or not? Can I do that? Can I put y equals to 1 here? Can or not? Why? Why? Huh? Doesn't what? Doesn't include? Yeah, it doesn't include. So can I put it equals to y in this case? Can I do that? Can I do that? Yeah, sure. Maybe the volume doesn't affect, but you violate something very important. Think again. What's the thing you violate if I put equal sign here? Function, yes, okay? Because you say that y equals to 1, I send to 1. But here you say y equals to 1, I send to 2. Okay, so I want to send to 1 or send to 2. Right, okay, so you violate the definition of function. Okay, so you will anticipate that when we do a next level, we also doesn't want to clash at the boundary. Okay, now I use the word boundary. Okay, so you have this something like the staircase. Yeah, staircase formula here. Okay. So how to compute the staircase formula? How to compute the volume under the staircase? You know how to compute? How? Length times height times length time length time width time height. But now we have different height, right? So how? The height is not even, right? This one is higher, this one is lower. So how? Yes. So you divide by 3 parts. So you divide into 3 parts. So you divide what do we call it? Okay. Call it R1, R2, and R3. So you split your R into R1 plus R2 plus R3. Okay, this notation not good. So let's use set notation. I equals to R1 union R2 union R3. So how you compute? So how you compute the integral? So you also split your integral to sum. Okay, let me say one last thing and then we will break. Okay, so I want you to observe something very special here. I want you to observe something very special here. This is the reason why you should do math. Okay, so you see, we split the set into unions, okay? But the integral come out as a sum. Okay. So you can see that this operation here, right? The addition of operation here. So union is somehow a plus. Addition, I mean. Okay. Through some operation. Okay. Yeah. And then if you observe more in mathematics, you will see that intersection will correspond to mod products. Okay. Yeah. Okay. So now you see that there are these transition between this operation, and then through what? In this case here, through the integral. Okay, so this operation is additive on the union of set. Yeah, additive on union of set. Okay. Yeah, I think you guys can compute the height, right? I will post out the solution later so you can compare. So you just compute the volume of your rectangle, then you'll get the answer. And then we will continue on Friday. Friday. Okay. Okay, so see you next time. I will post out the project announcement on how you submit it later. Okay, so turn it in. I heard that people saying that you cannot submit too many times, right? If you submit more than 3 times, then you need to wait for longer report. Okay, so only do it once you are done. Okay, you can try 3 times before you need to wait.
Oh.
等一下哦，有什么呢？哎，我怎么 stop 了？哎呀，太早把它拔掉。stop